This lesson is on U substitution, and U substitution is a method for finding our antiderivatives, and it reverses the chain rule. And so I'm going to go over the steps for it first, and you're probably not going to understand what I'm saying until we get to a actual example, but I want you to have these steps down first. So the first thing is you have to pick a good U. And by a good U, we're looking for something a lot of times that has a derivative inside the problem, and I'll show you what I mean by that when we get to our examples. But you're looking for something that you can see a derivative or part of its derivative in the problem. The second step is to take the derivative of our U, and we want to use the d over dx notation for the way that I teach you, and not use the U prime. It's my method of teaching you some of these certain steps, so we'll just all get in the habit of that. And then we want to substitute into our integral, and right now we're just going to be substituting back in. When we start into definite integrals, we will be changing the limits with those, and when we get to those, I'll make sure to bring that up again. Then we're going to take the antiderivative, because once we've substituted, it should be something that's simple to take the antiderivative of. And then for your final answer, you resubstitute back in for whatever your U stands for. So here is our first example. And again, we are trying to pick a U, and it's something where you see the derivative or part of the derivative in the problem. Notice that you have x cubed right here, and the derivative of that, 3x squared, is up front. That means that x cubed is going to make a good U. So let's come over and pick, you do this work on the side, this derivative work. Okay, so you do this derivative work over here on the side. Here's our U. Then we take the derivative, so the derivative of U would be du dx. And the derivative of x cubed is 3x squared. And then because we see exactly 3x squared in that problem, I'm going to leave that alone. But I am going to multiply both sides by dx. And that leaves me du equals 3x squared dx. Now all that seems kind of weird, but this is where we substitute in. In your problem, you have a 3x squared and a dx. And we have over here a 3x squared and a dx. So what we're going to do is substitute du in for both of those. Du is going to go at the back of the integral, because that's generally where we put that type of thing. But those things that are highlighted are what I replaced, so they're gone now. And I have left this cosine x cubed, but I chose x cubed as my U, so I'm just going to say that is the cosine of U. So I'm substituting in those yellow highlighted components for du, and then my x cubed was the U, so it got replaced with U. Now when you look at this problem, it's a whole lot simpler. Originally, the problem was not a rule that you know. Now it is a rule that you know. So the antiderivative of cosine of U would be sine of U plus C. You just taken that antiderivative rule like we've been doing with our basics. And then the final step is to substitute back in for U. Since U stood for x cubed, you rewrite that and say that is sine of x cubed plus C. And you'll notice if you took this derivative, sine of x cubed plus C, you would end up with the 3x squared times the cosine of x cubed. But that is the general process for this. Okay, our next couple of examples look a little bit different because you don't see a derivative in the problem like we saw that x cubed and 3x squared in the first one. But we don't know a rule for e to something that to a power that's not plain x. And so the fact that this power is a 3x, it means that that needs to be our u. So I'm going to come over here and I'm going to choose the 3x as my u. I'm going to take the derivative of that, so the derivative of u would be du dx. The derivative of 3x is just 3. Now, when you get to this point, you can go ahead and multiply both sides by dx and say du equals 3 dx, but you'll notice you don't have a 3 in the problem. So this right side needs to be the things that are actually there, and if they're not actually there, you want to divide by it. So if I divide by 3 on both sides, I get 1/3 du equals dx. The right side, I do have a dx in the problem, and so it is right here, and I'm going to replace that with 1/3 du. So the 1/3 and the du both go in for that dx. And then with my e to the 3x, remember, I'm going to take that 3x out and now call it u. Okay? And so this is now a rule that you can do because you're used to having numbers multiplied by e to the x or e to the u. The antiderivative of e to the x is e to the x. So the antiderivative of e to the u is e to the u, but it had a number in front, so we just bring that down. And here's my antiderivative, but I do need to resubstitute in for u. So 1/3 e to the 3x plus c is my answer. Now, I do want to mention that whenever you have a situation like this where we have a 1/3, I wrote it inside of the integral. You can write it outside and just think about that rule. As long as it doesn't have an x with it and it's a plain number, you can do that. That's something that is a property that you can use if you prefer it to look a little neater that way. And just remember to bring down your 1/3. That's up to you. Okay, so example 3 is really similar to that. You'll notice that we don't know the rule for sine of 5 theta. We just know the rule for sine of theta. And so since the derivative of 5 theta is not in the problem, that's okay. That's still going to be my u because I know the rule for sine. I just don't know the rule for sine when it has something other than a plane x or plane theta. So I'm going to let u equal 5 theta. And so I take the derivative, du d theta, because theta is our variable, will equal the derivative of this. And you just think of that like it's an x. Derivative of 5x would be 5. Derivative of 5 theta is 5. And again, if I multiply by d theta, I have du equals 5 d theta. And again, when I look at that, I have the d theta in the problem, but I do not have the 5. So I need to divide by the 5, and 1/5 du will equal d theta. So I'm going to take the d theta out of the problem and replace it with 1/5 du. This time I'll write that 1/5 out front and just show you that that's okay. So I'm replacing d theta with 1/5 du. Then I have sine of 5 theta, but I'm going to replace the 5 theta with u. And in this case, again, now I'm down to a rule that I know, and the antiderivative of sine is negative cosine. So I'm bringing down the 1/5, and I'm getting a negative, so I'm going to say that's negative 1/5 cosine u plus c. And then I just resubstitute. So negative 1/5 cosine of 5 theta plus c. And again, you can always check your answer, because if you take the derivative of this, you should get what was in that integral to begin with. Now, 4 is a little bit different. It's kind of like back to example 1, where I can see a derivative or part of the derivative in the problem. the derivative of t squared plus 1 would be 2t, and there's a t in the problem. There's not a 2t, but there is a t. So this is a situation where part of the derivative is there, and we'll work this out so you can see what happens when that is the case. So because its derivative, or part of its derivative is there, the t squared plus 1 makes a good u. So I come over and use t squared plus 1, and anytime there's like a plus 1, plus 5, plus a number, you definitely want to take it if you can, just because the derivative of that is 0, and it'll take that out of the problem. It won't be an issue anymore. Alright, we take the derivative, so du dt would equal 2t, and when I multiply by dt, I get du equals 2t dt. Now the problem is that, again, the 2 is not over here, just the t and the dt. So I'm going to do kind of what I was doing in those examples 2 and 3 and divide by the 2. So I have 1/2 du equals t dt. And now this over here matches what I have in the problem. And I have 1/2 du that I'm replacing that with, so I'm going to say 1/2 du replaces those t dt's, and then I just have e to the t squared plus 1, which I replace with u. And again, I'm going to take the antiderivative. So I'm going to bring down the 1/2, and the antiderivative of e to the u is e to the u. And I always put my plus c. And then the last step would be to plug in for u. So 1/2 e to the t squared plus 1 plus c. Okay, I'm going to do one more with you, and then I'm going to let you try some. Example 5, we have sine squared and cosine, and you might think of, maybe using trig identities first, see if that helps, but in this case it actually doesn't. So we go about picking our u, and in this case, the derivative of sine is cosine, and the derivative of cosine is negative sine, so you're making a choice of what to use as your u. But if you'll try those out in your head a little bit beforehand, you'll realize that you'll get stuck if you use cosine as your u, because there are 2 sines here, and that would only get rid of one of them. And so I'm going to use sine as my u. I'm not going to take the squared with it, because that would create more things. So my u is just going to be the sine of x. And then take my derivative, so du dx, derivative of sine is cosine. Multiply by dx, I get du equals cosine dx. And that matches the cosine dx in the problem. So I'm going to take that out and replace it with du. And then because I chose just the sine as my u, and the sine was squared in the problem, I have u squared. Now when I take the antiderivative, it is a power rule. So I have 1/3 u to the 3rd plus c. And then I'm going to resubstitute the sine. So 1/3 sine cubed x plus c. And that will be my answer there. Okay, so here we have example 6 and example 7, and this will be a great time for you to pause and try these on your own. Okay, for number 6, your final answer should have been 1/3 e to the x cubed plus c. The best thing to pick for the u is the x cubed, because the derivative of it is 3x squared and there is an x squared in the problem. When you take the derivative of the x cubed, you get the 3x squared. You have to end up dividing by the 3 because the 3 is not in the problem originally. And you end up with the x squared dx matching the x squared dx from the problem. So you substitute in 1/3 du for the x squared and dx, and then the u for the x cubed, so it gives you 1/3 integral e to the u du. The antiderivative of that would be 1/3 e to the u plus c, and then you plug back in for u. So that one was a partial derivative kind of problem. Okay, example 7 is another one of those where you see part of the derivative in the problem. The derivative of x to the 4th plus 5 would be 4x cubed, and there is an x cubed in the problem. So that makes the x to the 4th plus 5 a really good u. So I chose that as a u. Take the derivative, we get du dx equals 4x cubed. The 5 goes away. That's one of those situations I say take it with you because the derivative of that is 0. Now, there's not a 4 in the problem, so I went ahead and divided by 4 when I multiplied by dx. So I got 1/4 du equals x cubed dx. The x cubed dx is in the problem, and so I'm going to replace that with 1/4 du. And then my u, my x to the 4th plus 5 that I turn into u, is under a square root. And since we're getting ready to take an antiderivative, I want to turn that into a power. And so that is going to become a 1/2 power. When I take the antiderivative, I am bringing the 1/4 down. I am doing the power rule with the u. So I wrote it in parentheses to show you I added 1 and got 3/2, divided by that in front, got 2/3. And then I go ahead and multiply the 1/4 times the 2/3. And get the 1/6 in front, and then I resubstitute in for my u. Okay, we have our last two examples. First of all, number 8. People mess up problems like this because they think, well, the derivative of e to the t is e to the t, and so I could use either one. This, because it's on the bottom, you have to remember that's technically to a negative power. So the best one to choose for your u is the bottom, and you'll see why in just a minute. Again, it has that 1. Take it with it because the derivative of 1 is 0, and that's going to go away. It's not going to be part of your issue anymore. So I'm going to choose that as my u, and the derivative of u would be du dt. Derivative of 1 is 0, derivative of e to the t is e to the t. And so when I multiply by dt, I have e to the t dt. This is what matches the problem. It matches this e to the t dt here. If I had gone the other way, I could not have canceled out that bottom because technically that is to a negative power, and it would not work. I would have to have an e to the negative t over here when I work the derivative. So I'm going to take out the e to the t dt, replace it with du, which means there's nothing left on top of that fraction, so I put a 1. The bottom is my u, so I have 1 over u. And this is the case where you have to remember this is not a power rule, this is your natural log rule. So this is the natural log of the absolute value of u plus c. And then finally plug back in. And this will be a case where actually the absolute values would not be needed because 1 is always positive and your e to the t graph is always positive. So if you were working something out, you could actually get rid of the absolute values because everything inside will always be positive. Okay, the last one, tangent, seems like it doesn't fit because it doesn't look like there's a chain rule in here. And so you almost don't know what to do. But you can actually change tangent into sine over cosine using your identities. And this becomes a problem that you can work with u substitution. So I'm using that identity first, and this is kind of like example 8. I need to choose that bottom as my u so that I can cancel out the top. So I'm going to use u as cosine theta. My derivative would be du d theta. Derivative of cosine would be negative sine. And since I don't have a negative in the problem, I'm going to divide by the negative when I multiply by the d theta. So I'm going to have negative du would equal sine theta d theta. Now I do have sine theta d theta in the problem, and I'm going to take those out and replace them with negative du. So I'm going to pull that negative out front because it's just a -1. And since the sine is gone from the top, I have to put a 1. And the cosine was my u, so I'm going to turn the bottom into u. And again, I have that natural log rule coming up. Just make note that anytime this is a power other than 1, so if this was 1 over u squared, that would be a power rule, not a natural log rule. So I'm going to bring down my negative, and I have the natural log of the absolute value of u, and then I'm going to plug in. This would not be a case where I could get rid of the absolute value bars because cosine is sometimes negative. It would depend on the situation that I was looking at, whether I could get rid of them or not if I was trying to solve. So these last two, again, were the weird situations with fractions, but that does conclude this lesson.